Okay, so this is the physics first test review from 2016 through 2017. So this is chapter 1 through 5 test review. And I'm just going to go through all 10 questions and just walk you through the way that I would do them. If you have questions about it, please come in and see me, or maybe look at how you've done it before on your own and maybe compare it. The first question says you want to know how much mass your car has, but you don't want to take it to a scale. You know that when you pull it with a force, let's pull it with a force equal to 100 newtons, that it accelerates at a rate of 0.143 meters per second squared. And the question is, what is its mass, and then what is its weight? Okay. The mass value is actually really easy to find because we know the sum of the forces, F, will always equal ma. Now it says to ignore friction, so there's no pullback. There is a normal force because your car sits on the ground, but that should cancel with gravity. So the weight of the car and the normal force should match, and then of course we have the 100 Newton force pulling you sideways. And so the only force that we really have is the 100 equals 0.143 times A. If you divide by 0.143, or sorry, that's backwards. That's the acceleration, that's the mass. So let me switch those. This should be an M, not an A. And so 0.143, if we divide that, we get the mass, my fault, will be equal to roughly 699 kilograms. Okay, so we get the mass of the car. To find its weight, we just times by 9.8. If you times that by 9.8, you're going to get a weight of approximately 6,850 newtons. Okay, so that's the weight of the vehicle as compared to its mass. Question number 2. Lexi's serving a volleyball. Here's the volleyball. Of course, it's in the air. Yes, gravity is pulling down, but we're going to pretend for a moment that this is at its highest point, or at least that the up-down motion is not going to determine the speed with which it leaves her hand. Because when her hand makes contact with the ball, it's going to stop any of its motion and then redirect the ball. So let's just assume that she hits it horizontally. So there's a force of 65 newtons. Okay? The ball has a mass of 0.55 kilograms. And we're being asked, and so we also know that the time that her hand is in contact with the ball is 0.25 seconds. Okay, and so the question is, how fast is it moving when it leaves her hand? Well, the first thing we have to understand is that this ball is not going to stay at the same speed the whole time. In fact, one of the first things we might want to recognize is that when her hand hits it, we're going to say that it has a speed or a velocity of 0. That's kind of a key point. Now we know that it's in contact with her hand for 0.25 seconds, and we want to know the final speed. Really, the missing piece here is the acceleration. And that's where the other information comes in. Like question 1, we know that F equals ma. So in this case, 65 will equal 0.55 times the acceleration. If you divide by that 0.55, the acceleration the ball experiences is 118.182. And now if I go back over to here and do the kinematic formula, I'm going to use the first one. V equals V naught plus AT. V naught we already said was 0, so the final velocity will be 118.182 times the time of 0.25, and that comes out to approximately 29.5455, which, because of sig figs, we round to 30 meters per second. And so that would be the speed of her serve, how fast the ball is coming off her hand. Question number 3, we have a box. Of course, gravity pulls down on it, and the normal force pushes back. Because it's on a horizontal surface, they should be equal. You have the applied force, which equals 400 newtons. But then you have, of course, the force of friction. And we don't know what the force of friction is, but because we're told the box doesn't move, we know that the force of friction and the applied force have to be equal. They have to cancel each other. So that means the force of friction, which we have defined as mu times the normal force, But because this is on a horizontal surface, we know the normal force and mg have to be equal. So the force of friction is really mu mg. That's our force of friction. But we know the force of friction, in order for this to not move, has to be equal to 400 newtons, because these two forces have to cancel out over here. Well, that makes mu times a mass of 200 kilograms, that was given in the problem, times, of course, 9.8 equals 400. 200 times 9.8 turns out to be 1960. So if we divide both sides by 1960, mu is going to be 0.204, which I think that 200 kilograms and 400 newtons is probably 1 sig fig. I would accept this because 200 and 400 could be 3 sig figs. But mu, I'm going to just come out and say is 0.2. Question number 4. Miriam is going to go to Mars. Okay, she has to travel a distance of 54.6 times 10 to the 6th kilometers. To make this in meters, I'm going to move that up 3 to 9 meters. I know that the speed of my rocket, or my space travel, is going to be at 2430 meters per second, and I'm being asked how long will it take. If I look at this information, I can kind of decide that, hey, if the space shuttle doesn't accelerate, meaning it's always at the same speed, and I say 0 there, I might be able to solve an equation. Now, using the kinematics. Now, if the acceleration is 0, then this is also equal to v naught. Okay, v naught would be the same as later on. There are multiple ways to do this. This is really a distance equals rate times time question, but within the kinematic world, I can say delta x equals v naught t plus 1/2 at squared, but I know that a is 0, so that doesn't matter. So the 54.6 E9 equals 2430t. If you just divide by the 2430, t is going to come out as a really large number. It's going to be roughly 2.25 E7, but that's in seconds. So I want to convert that into probably days. So I'm going to divide that by 3600 to get hours, and then whatever I get I'll divide by again by 24, and I'm going to get roughly 260 days when you round to 2 sig figs. So that's about how long it's going to take me to get to Mars, just under a year. But that's only under the circumstance that I go that fast and that I do it when it's at the closest possible value. If we move on, question number 5. This is one of the more challenging questions. Okay, you have a 2-meter drop when you throw a baseball, and it's got to go 18 meters across as it falls. And the question is, first off, how long is it in the air? And then also, will it make it to 18 meters before it bounces or not? Okay, so the first thing I want to do here is I want to build my x and y information. This is a ball flying through the air, so I know it's projectile motion. Projectile motion questions always get set up like this: x information, y information. And I'm thinking about the kinematics. V naught in the x direction, if we read the question, is 32 meters per second. But that's also the final speed, because in the x direction the acceleration is 0. But you can't use both v's, so I'm going to ignore the second velocity. Delta x, I don't really know if it makes the 18 meters or not, so I'm going to leave that alone. And then the t, I don't know. Over here in the y information, in the y direction, I'm hoping that when we throw horizontally, that we get 0 velocity. The final velocity, I don't know. The acceleration is 9.8, and the delta y, I know it has to fall 2 meters. The t is an unknown. So I'm going to take the y information and put it in the second kinematic. 2 for delta y equals v naught t, but v naught is 0, plus 1/2 at squared. 1/2 of 9.8 is going to be 4.9. Okay. t squared. If I divide by 4.9 and I take a square root, t will come out as 0.64 seconds, roughly. And so we will take that 0.64 seconds as our first answer. Well, now that we know this is 0.64 seconds, we can come over here and find the delta x. So in this case, delta x equals v naught, that's 32, times t, which is 0.64, plus 1/2 of 0 times 0.64 squared. But because of the 0, all of that is gone. So delta x turns out to be 20.4 meters. Now, this is not the answer. The actual answer is, yes, it crosses the plate. Okay? It's going to cross the plate because it moves more than 18 meters. Now, there was a bonus question in the original test question, which was, how high off the ground is it going to be when it comes over here? So if this is 18 meters, the back of the plate, how high off the ground is it there? The way we would do that is by taking the same problem, but delta x I would make 18. I would solve for my time. Once I know my time, I could plug that information in and go at it that way. Okay, so we won't worry too much about that right now. Question number 6. Evan's flying his pilot license, so he's going 120 meters per second north, and there's a wind that pushes him west 5.2 meters per second. The question is, what's his actual course and how fast is he flying? There's a 90-degree angle, so I want to know what's his angle of deflection and also what's his actual speed. The speed part's easy. It's 5.2 squared plus 120 squared, all inside of a square root. This is going to come out to 120.113 meters per second, and because of sig figs, which is only 2, I have to round this to 120 meters per second. I know deep down it's really a little more, but it's not very much more. Then the last part for me is to find the angle. I know that the tangent of my theta is the opposite 5.2 over the adjacent 120, and if I take the tan inverse of that information, I'm going to get that's 120 degrees at 120 meters per second, sorry, at 2.5 degrees west of north. Now, you could just say deflected to the west or things like that. You don't have to say west of north. You could draw it in the picture, and label west is this way and north is up here. You say, I'm deflecting to the west. Something along those lines. Just make it clear which way I'm being deflected. Question 7. Question 7 says I've got a marshmallow. I'm going to spin in a circle. Okay. It's a horizontal circle though, so think of it kind of like you're spinning it over your head in a sling. And so there's a string attached to it. And the question we have is, how much force do I want to apply on the string? How much do I want to pull inward to create this circle? Well, let's go through some information. First off, as soon as you see circular path, you want the force to equal mv squared over r. That has to happen. And since that's the question we're actually being asked, how much force do you apply, this will be the answer to our problem. The marshmallow has a mass of 0.0012 kilograms. The velocity I'm spinning it at is 15 meters a second, but that's got to be squared, all divided by a radius of 2 meters. Honest to goodness, you just plug it into the calculator and you're going to find 0.135 newtons, which simplifies down to 0.14 newtons when you do sig figs. All right, just 3 more, 8, 9, and 10. Question number 8. Oops. Okay, we're trying to figure out the amount of gravity, little g, on Pluto. If you're looking for little g, you're going to use the big force equation for gravity, which is g m1 m2 over r squared. But what you have to remember is that this is a force. G is not a force. mg is a force. Okay. In order for me to find little g, I'm going to need to divide by this m, which should cancel one of the m's. Specifically, it cancels the m of the smaller object. So little g for any planet is 6.67 e negative 11. We want to times that by the mass of the planet we're on. In this question, we're told the mass of the planet, Pluto, is 1.30 e, and there's a typo. It should be e22, not 24. All over. Okay, and so then we need the radius of the planet Pluto, and there was another typo there because I said I gave you the radius, but what I gave you was actually I gave you the diameter, but it's really the radius. So 1.19 e, and we're going to go 6 because it is kilometers. We need it in meters, and then of course that gets squared. All right, so what we're going to do is we're going to plug all of this in the calculator. Now, when I put this in the calculator, I want to be really careful. Make sure everything's typed in properly. Definitely want to use that E key, so turn it on. 6.67 second E negative 11 times 1.3 E 22. And then I want to divide that by 1.19 E6, but I need to square that, so I'm going to just come and insert some parentheses and then come back and square it. I really need to make sure that gets squared properly. And when I do, I get 0.612. Because of the 3 sig figs, I'm going to say that it is 0.612 meters per second squared. It's a very small amount of gravity on Pluto. The next question we have is number 9. It's about the velocity of a satellite. And when you see satellites and objects like that, VSAT is square root of GME, or whatever planet we're on, over R. So it's really important when we do this, we make sure that we are on Earth. If we're not on Earth, we need the mass of the planet that we're on, or that we're orbiting around. Other than that, this is just as straightforward. We're going to type in G, which we know is 6.67, E negative 11. The mass of the Earth happens to be 5.98 E24, all divided by the radius of orbit. Now the radius of orbit, you have to remember, includes the radius of the Earth plus the distance out to the satellite. So it's really 2 parts. The radius of the Earth is 6.38 E6. We need to add to that, it says 2,400 kilometers, so I need to add 3 zeros. So if I add the 2 of these, I'm going to get 8, 7, 8, and then 0, 0, 0, 0. I think that's right. There and there. The 2 and the 6 add. There you go. So I'm going to put this all into the calculator. Again, when I put this in, I want to be a little cautious. I'm going to start with this one just because it's got the first part. I'm going to come over and make this 5.98 E24. And hit enter. Divided by 8780000. Hit enter. And then I need a square root of that answer. And I get 6740. Because of the 3 sig figs, well, it could be 2 sig figs, it could be 3 sig figs. That 2,400 is really the only number you were given. So I'm going to assume that it's 2 sig figs and go with 6,700 meters per second. Last question is question number 10. And there was a typo. When we say that the radius of orbit for Neptune is 4.5 times 10 to the 12th, that is in meters, not kilometers. So radius of Neptune is equal to 4.5 E12. Okay, this is a Kepler's law equation, which gives us the t's squared and the r's cubed. So we have to know a couple of pieces of information. First, we're trying to find out the time for Neptune. So we're going to compare that to the time for Earth, which is 1 year to get around the sun. Over here, we're going to use Neptune's 4.5, E12. But down here, we need to use Earth's radius of orbit. In the book, that's recorded as the distance between the Earth and Sun. And on average, we're going to run with the number 149.6 E. And it says in the textbook, it'll say E6 kilometers. So I need to move this to E9. Okay. To solve this question, we're going to get rid of the 2, and then whatever's in the denominator here, we times by. It's 1. We don't really need to times by it, but if we put this in the calculator, 4.5 E12 over 149 E9, hit enter and raise to the 3/2, you're going to get 160. Is it 4 or 5? Let's take a look. 4.5. Whoops. 4.5 E12 divided by 149.6 E9. Get an answer. Raise it to the 3/2, and we get 164.97. I'm going to round that to 165. It takes 165 years for Neptune to get around the Sun. I hope that's enough to kind of give you a baseline. Come in and ask questions if you get stuck. Thanks.